And I would like to invite the next speaker. Is he present? Is, if I'm not wrong, Nuttapol, are you there?
Okay, Professor, I am here.
Okay, it is my pleasure to invite a fresh PhD holder, Nuttapol Pakkaranang, who spent research visit to Baia Mare. Please share your screen and make your presentation.
Okay, can you see my presentation, Professor?
It's all right. Yes.
Okay. Okay. Good afternoon from Thailand. So my name is. Thank you very much, Professor Bernay, to invite me to be general speaker in this workshop. It is the second time of me. The first time I have ever been to talk in Baia Mare. I am very happy to first visiting in my life in the Europe at the Romania. Today I would like to talk about the topic of my research on solving minimization problem and fixed point problem for non-evasive mapping in geodesic space. Sorry. Sorry. Okay. The outline of this talk. The outline of this talk, I divide my talk to the four sections. The first section is the scope of this research paper. The next is the introduction and motivation. The next is the preliminary, and the last is the main result. For the scope of this research paper, I study on the geodesic space, in particular in Cat1 space, to find the common solution of the problem in minimization problem and fixed point problem. I got the motivation from this paper. Professor Chorlampiak study the proximal point algorithm involving the fixed point iteration for non-evasive mapping in Cat0 space. Next, I will talk about the introduction and motivation. The initial of term CATR honor from Professor Katan Alexandrov and Toponokov, who have made important contribution to understanding of the curvature via inequality of the distance function. Next, I will talk about the definition of geodesic path. A geodesic path joining x belong to x and y belong to x. Briefly, geodesic from x to y is a map gamma from a closed interval 0L is the subset of R to x such that satisfy two conditions. This is the figure from this definition. So particular gamma is isometry and distance xy equal to L. Next, the image of gamma is called the geodesic segment joining x and y. The space x is said to be a geodesic metric space or geodesic space if every 2 points of x are joined by geodesic. When it is unique, this geodesic denotes by this. Next, I will talk about the comparison triangle for geodesic triangle in XD. is a geodesic triangle satisfy this equation. So the left hand side is the geodesic triangle and the right hand side is comparison triangle in R2. Next, a metric space is called cat-zero space if X is geodesic metric space, and every geodesic triangle in X and its comparison triangle satisfy this inequality from the reference number 1. You can see the picture on the left hand side is the geodesic triangle in X, and the right hand side is the comparison triangle. Next, if X, Y1, Y2 are the point of cat-zero space and Y0 is the midpoint of the segment Y1 and Y2, we will denote that Y1 over Y2 over 2, then the cat-zero space inequality implies this inequality. Inequality number 1 is called CN inequality. You can see the detail from reference number 2. A geodesic metric space is a cat-zero space if and only if satisfies CN inequality. The further complete cat-zero space is called Hanama space. Next, I will talk about the general line of the cat-zero space. The first, we will call the definition of a uniquely pi geodesic path. So let's XD be a metric space joining X belong to X and Y belong to X are the map gamma in this code interval. But distance XY less than pi such that satisfy two conditions. In particular, C is isometric and XY is equal to gamma T and a geodesic segment between X and Y. So in Hilbert sphere, define the spherical metric like this, and H and low HH is a uniquely geodesic complete metric space. So in particular, if XY belong in H, and then the unique geodesic path from X to Y is given by this. We denote by S2 in the model space. Next, a metric space equal the cat1 space if X is a uniquely pi geodesic and satisfy the C1 cat1 inequality. This is the figure to explain this condition from reference number 3. Next, in 2003, Professor William Arthur was proved the existence of the fixed point for non-explicit mapping in cat-zero space. And later, Professor Espanola extended the existence of the fixed point result of the Professor Clerk to cat-1 space. In 2013, Professor Kimura using MAN algorithm to approximation the fixed point of non-explicit mapping. On the other hand, Professor Roccapella studied the proximal point algorithm, which introduced the first by Professor Martinez for solving the minimizer of a certain on the convex function. So the proximal point algorithm defined by this from reference number 7 and 8. Next, in 2013, Professor Bachak studied and extended the proximal point algorithm in Hanama space or complete cat-zero space. The algorithm generated by this. He proved that if F has minimizer and then the sequence Xn delta convert to its minimizer from reference number 9. Later in 2017, Professor Kimura and Professor Kosaka introduced the proximal point algorithm in cat-1 space, define the proximal operator to find the solution of the minimization problem like this. They proved that F has minimizer and satisfy this condition, then the sequence xn delta convert to its minimizer. This is the motivation of my research in this paper. I would like to extend to find the common solution of fixed point problem and minimization problem from cat 0 space to be cat 1 space. And then I will prove the delta convergence of the proposed algorithm under some mild condition. Next, preliminary. Okay, for this section, I will recall about the definition of fixed point and the definition of approximating fixed point sequence defined by this. Next is the well-known mapping is called non-evasive mapping defined by like this. Next, for the proof the delta convergence, we have to add some condition is called the admissible, so defined by like this. Moreover, if the sequence xn in cat 1 space is spherical bounded if satisfy this inequality. The next, I will talk about the Lesoven operator in cat 1 space. Let G be a proper lower semi-continuous and convex function for all lambda greater than 0. We define the Lesoven operator like this. In particular, the set of f of the fixed point of the Lesoven associated with G coincide with the set of the argument min of the minimizer of G. Next, the lemma 2.3. Let XD be a complete cat 1 space and the sequence is spherical bounded if distance xnu is convergent for all u belong in delta, then a sequence xn is the delta convergent. And the lemma 2.4, this is the definition of delta lower semi-continuous in cat 1 space. And lemma 2.5, this is the lemma to prove the delta convergence. We will call the demi-closed-net principle. Let C be a non-empty and closed convex subset in complete cat 1 space. Let C be a non-evasive mapping if xn is the bounded sequence such that satisfy this is called the approximate fixed point sequence from reference number 12, 13, and 14. Next, the main result. This is the step proof of my main result. The first, in step 1, we will prove the sequence xn is exists, and next we will prove the xn and zn limit equal to 0. And in the step 3, we will prove the approximate fixed point sequence for non-evasive mapping. For the last step, we will use the demi-closed-net principle and the delta lower semi-continuous to prove the delta convergence. This is the statement of my result. Let XD be admissible in cat 1 space and G be a proper lower semi-continuous convex function. T is the non-evasive mapping, and we assume the set of fixed point and intersection with the set of solution of argument min of the function G is the non-empty set. We assume that the alpha n satisfy this condition, and then the sequence xn be generated in algorithm 2. Then we will get the assumption S1, S2, and ST. The next, this is my main theorem. Let XD be a admissible cat 1 space and G be a proper lower semi-continuous convex function and T be a non-evasive mapping such that the set of fixed point intersection with the set of minimizer of the convex function G is the non-empty set. We assume alpha n satisfy this condition. So the sequence xn be generated by algorithm to then the sequence xn delta convert to an element of the common solution of the set of fixed point. Thank you for your attention.
Thank you, Nuttapol, for the interesting presentation and for using exactly your time. Actually, we have half a minute for questions or comments, please. No questions? Then I congratulate Nuttapol for succeeding to finish the thesis, to being successful with defending it and having now the title of PhD holder. And I hope all PhD students present here in the workshop will succeed to finish their thesis. Thank you, Nuttapol. Good luck and great success in your professional activity. Thank you.
Okay. For now, I would like to happy to inform you that now I get the job in the university in my hometown.
Great.
Yes,
It's a great news. Congratulations.
Yes,
I'm very happy about this.
Yes,
okay, good luck.
Thank you.
I plan to visit you when all things will be
okay.
all right. Okay,
welcome.
thank you for your presentation.